Well, I'm very honored to be here, thanks to the invitation I received from Dr. Varun and Lakshmi Praturi. Without their generosity and kindness, persuasion, I wouldn't be here. Long way to come to give a lecture from California. Anyway, here I am. I'm going to talk to you about the human brain and its functions. A topic that's fascinated all of us for centuries, especially this last 2 or 3 decades. There's been an explosion of research on the human brain. Much of it is just gathering facts about the brain, which is a useful activity, but doesn't in itself doesn't solve the problem. You begin with facts first, said somebody. Then you come up with theories to explain the facts. But this is fallacy. We are not cows grazing on the pasture of knowledge. Peter Merwa said, science is an active process, creating conjectures, testable conjectures, and then going on to test them systematically. Stating the obvious here, but I'm going to give you many examples of strategy used in the functions, studying the functions of the brain. Okay, I'm going to go slowly because I tend to speak fast and I'm jet lagged. Okay, think about the problem you're confronted with. You've got this mass of jelly, 1.5 kilograms, which you can hold in the palm of your hand. Consistency of pudding, same color as pudding. And this squishy mass in your hand can perceive objects, events, perceive other people, recognize people, can experience emotions, sorrow, jubilation, anger, ambition. You can also contemplate itself, contemplating. How does this happen? The so-called self-awareness. This is one of the most mysterious aspects of the brain, introspection. One of the most mysterious aspects of the brain. Right? How does all this come up from the lump of jelly? How does this whole spectrum of experiences we call consciousness emerge? That's the problem before us. And I don't think you can solve this by taking the problem in the abstract. Consciousness, let's discuss it and figure it out. You can't do that. The key is to do experiments. And there may be a turning point in the history of science when you finally figure out how the brain works. You still don't, just scratching the surface right now. I'm going to spend the next 2 hours or 1 hour scratching the surface. But hopefully the noise will be pleasant. Okay, how do you study the brain? Many approaches. One approach is what we call the localizationist approach. I don't actually have to move there, sorry. How come this is not working? It's not moving this way. Yeah.
Yeah, it's moving there.
Moving there, but it's not moving.
No, so the slides there will be moving. So they have.
Oh, I see. You guys can see that? Okay. At first I thought it had a lesion. Okay, so it's very, very strange. I'll put some, okay, so what we do, the brain consists of 100 billion neurons. Everybody here in AI, physiology, biology knows this cliches, but since I gave the talk yesterday to a non-specialist audience, I have this canned introduction. 100 billion nerve cells, give or take an order of magnitude. Each nerve cell makes 1,000 to 10,000 points of contact with adjacent neurons called synapses. Each synapse can be off or on, inhibitory or excitatory. Someone has figured out that the number of brain states, elementary particles, in the brain states exceeds the number of elementary particles in the universe, the known universe. Staggering complexity you're dealing with. How do you begin to study this mysterious organ? Well, one approach is to do brain imaging, find out what parts of the brain light up when a particular task is performed, specific task, and do not light up. Then come to draw conclusions about that the brain, that function is mediated by that region. It can be very misleading because imaging is full of artifacts, but sometimes it gives you good results. It's very expensive too, bear in mind. So we've been doing some of that, but mainly what we do is behavioral neurology, 19th century neurology. I'm going to take you back 100 years, 19th century. Experiments could have been done, what I'm telling you about could be done, Aristotle. Well, you can go back 2,000 years. Aristotle could have done most of these experiments, not all of them. What I'm going to tell you about. Let me tell you one example. Condition called interpersonal gagglesthesia. I tickle myself, you're watching me tickle, you're not going to laugh. You can't tickle yourself either. You cannot tickle yourself. If I tickle and you watch, you don't normally laugh. But there's a group of people who laugh uncontrollably when I tickle myself and they watch. This is a medical mystery of sorts. Why would somebody laugh uncontrollably when they're watching me tickle? And I'll explain it as we go along. The name of the game is to find patients with peculiar disturbances of the mental functions and then explain the peculiar disturbance. What causes it? To the patient. Patient often deeply grateful when you tell them this is what's going on. You're not mad, you're not crazy. This is what's going on in your brain. So when there is a damage to a specific location in the brain, a small lesion, what you lose is often a highly specific function, with other functions being preserved, not a general attenuation or dumping or silencing of the entire brain. You don't get decrement in function of all functions. You get one specific functional loss. Right? That gives you confidence in asserting that region of the brain is mediating that function. That's the first approximation. That's where you start. I'll give you several examples of this today, of our successes and our failures, but let me start with one success story. Phantom limbs. You all know what a phantom limb is. If you amputate an arm, you feel the presence of the missing arm continuously present, sometimes excruciatingly painful. The phantom is painful, fingers clenching into the palm, ow! There is no palm, there is no clenching. It's all in his head, so to speak, but not psychological mumbo-jumbo. He knows it's abnormal, he wants to get it corrected. It's not a psychological phenomenon. It's a delusion of sorts. It's a physiological delusion of sorts. What causes it? We'll get to that in a minute. We had a patient come into our office. By the way, we can have phantom with any part of almost any part of the body. Phantom arm, phantom finger, phantom foot, phantom genitals. You get even phantom erections. You can get phantom uterus, phantom menstrual cramps. And some student once asked me, if you get phantom menstrual cramps, do you also get phantom PMS? I don't know the answer to that. Okay, so maybe they do, maybe they don't. I don't know the answer. Okay, the next question is, how do you study these patients in the laboratory? Very simple. What we do in our lab is very simple experiments, but yielding often very interesting results. Not always, but sometimes. Then you hit the jackpot. We'll give you one example. This patient comes to me, left arm is amputated above the elbow, missing arm, vividly feels the presence of the arm, the phantom arm. He says, I said, put your hands on the chair. Okay? I'm going to touch various parts of your body and I'll ask you what you experience. I took a Q-tip, cotton bud, chap is sitting in a chair, blindfolded. I touched different parts of his body. What do you feel? My right shoulder. The left arm has been amputated a couple of weeks ago. Left phantom arm. That's my left shoulder, doctor. That's my belly button. And he laughs, giggles, obviously. What about that? Well, that's my left shoulder. And he's bored by now. What about that? Oh my God, you're touching my left phantom thumb, my phantom thumb. Phantom index finger, phantom pinky, phantom ball of the thumb. Complete map of the missing hand on the face. Why the devil should this happen? The mystery fit for Sherlock Holmes. Why would somebody, when you touch his face, feel it in the hand? It's sort of neuroembryology going on here. So we said, why this happened? Okay, we looked at Penfield's diagram, famous diagram. If you look at the vertical strip of cortex behind the central sulcus in the parietal lobe, vertical strip of cortex, in that strip there's a complete map of the body surface on the surface of the brain. Let me show you. That's a map in a coronal section. You see that different parts of the body are represented on different points along the brain surface, right? Genitals, toes, neck, shoulder, arm. It's a systematic map. Now notice some peculiarities of the map. The head and face, instead of being near the neck where it should be, is dislocated below the hand. Why that is, we don't know. Notice how the feet are below. The feet are below the genitals. This may be very important clinically. Get to it in a minute. Okay, now what's happened in this chap, in my theory, when you amputate the arm, this map becomes hungry. I can't use a pointer here, that's a problem. You want to visualize the map. You see the map? You have now removed the input coming from the hand to the hand area, middle index finger, thumb, the area in the middle of the strip. Everybody sees the area in the middle of that strip. Complete representation of the body. Hand area now receives no input because you amputated the hand. So the input coming from the face skin, normally activating face area, invades the vacated territory corresponding to the missing hand. Correct? Invades it and then activates the cells there. Whatever is reading the signals up higher up misinterprets the signals as arising from the missing phantom limb. So when you touch the face, message goes and activates the face area, but also invades the hand area, activates cells there. The patient misinterprets it and says it's coming from my, mysteriously emerging from my phantom hand. He touches his face, and he's very surprised by this. Now then, so what? Well, the reason it's important is it's telling, in all our studies, discover a syndrome, 4 questions in mind. First, define the syndrome. What are the symptoms? Is he making it up? First question. Is he confabulating? Sometimes patients just make up stories for insurance purposes. Is he confabulating or is it a real phenomenon? Second, if it's real, what's causing it in the brain? Can it tell you something about normal sensory processing? Third, well, so what? Okay, you discovered this little quirky phenomenon, phantom limb, something going on in the brain. Why should I care? Right? The answer is sometimes you discover the mechanism which explain not only his symptoms, but are generalizable to all brains, understanding normal brain function, if you're lucky. Fourth, you can discover a cure for it, if necessary. You don't want to cure synesthesia. I'll tell you why in a minute. But phantom pain is very serious. Some of them commit suicide, become profoundly depressed, lose their jobs. The pain in a phantom is intractable, chronic pain, very difficult to treat. So that's basically showing the plasticity, malleability of connections in the brain. The normal dogma, about 15 years ago when I was a student, medical student, the preceding 30 years, 40 years, the dogma had been neural connections are laid down in the fetus by genes or early in infancy, and they cannot be changed in the adult brain. Once they're laid down, that's it, kaput. It's hardwired. You cannot, and this lack of plasticity or malleability of brain connection is also often invoked to explain the notorious resistance of brain disease to recovery. The lack of recovery after neurology. Neurology is a gloomy profession on the whole. But we say that's nonsense. You're talking about 2 centimeter distance from the face to the hand, 2 centimeters of cortex. There's been a reorganization of the brain. In fact, you can show it using brain imaging. We showed it also doing brain imaging, confirming the map idea, the map change idea. But in science, often it's good to challenge yourself. Okay? Now, I'll tell you one example of this. So I've been telling you here for the last 5 minutes that the head is near the face, near the hand. Therefore, when you remove the hand, input from the face skin invades, cross-activates cells in the hand area, right? There's something wrong with that explanation. Because when you look at the patient, where is the map? Anybody, where is the map? On the cheek. Nothing on the forehead. Now, if that's true, how come the head is that, you see the orientation of the head in the map, it's the forehead that's near the hand, not the cheek. So I was being glib and saying, look, it works beautifully, it's in the, the map is there, fine, but the map is not in the exact right place, it's not in the forehead, it's in the face. How do you explain this? I said, well, who made this map? Made by a famous Canadian surgeon named Penfield. Canadian neurosurgeon. He put electrodes in people's brains and stimulated neurons, asked them what they feel. Ow! No, actually, he doesn't say ow. Under anesthesia. You put the needle and he says, my finger is tingling, my thumb is tingling, my elbow is tingling. So he makes a map of the surface of the brain. Now, either he got it wrong, putting the head, the particular orientation, or I'm wrong with my Q-tip, spent half an hour on the patient. So he's a surgeon, I'm a scientist, he's wrong, I'm right. And I said, this can't be explained any other way. The head, he got the head upside down. When you look at the original results that he's published, very few data points he had. And based on those, he's drawn this diagram. It's iconic of neurology, this diagram. Iconic of neurology. Now, what happened was, I then had a professor at Stanford in the audience, Steve Engel, said, I can test your idea in next week. I'm doing functional brain imaging on normal people, somatosensory maps. And he said, you want to collaborate? I said, I don't want to collaborate. You do it and tell me what you find. He went home to Stanford. A week later, he phones me and he said, my God, Rama, you're right. The head is drawn upside down by Penfield. This means all the medical textbooks you read from now on, neurology textbooks, psychology textbooks, physiology, this map should be redrawn. It's wrong. Head should be the other way around. Now, this is fun because even though it's not of great theoretical importance, what does it matter if the head is upside down or right side up? But I'm especially fond of this observation because of sadistic reasons. Not often you can come with a Q-tip and correct 100 years of anatomy. That's what makes it interesting. Okay? Now, another problem with phantom limbs is pain in the phantom arm. And we devised a technique which I don't have time to describe. Sorry about that, modern technology. I don't even know how to silence it. It's an old phone. Okay, we hope it doesn't ring again. Okay, so phantom is often cramped, painful. You don't know the origin of this pain. Patient says, I can't move my hand, doctor. If I move it, it might relieve the pain. It's in this awkward position. So we devised a simple technique of putting a mirror in a box. The patient puts his left arm, phantom arm, in the mirror, puts his right arm on the right side of the mirror, sees the reflection of the intact hand in the mirror, superposed optically on the phantom. Is that clear? From the diagram? Oh, sorry. Here. Oh.
No.
No?
You can see that's on the screen and they have it on the screen.
Okay, good. Sorry about that. You put a mirror there, and the patient looks in the mirror, moves his normal hand, attempts to move his phantom, which is paralyzed, quote unquote. Then the phantom looks like it's moving because it's a mirror image. But in fact, it starts moving. The patient says, my God, I feel my hand moving for the first time in 3 years. It's wonderful. And the pain goes away a lot of the time. In about 2/3 of cases, the pain goes away. With repeated treatment, 2 out of 3 patients recover from phantom limb pain. It's now widely used in hospitals throughout the world. Just this $2 mirror instead of virtual reality, which costs $100,000. Same. Okay. Next question. Now, there's been controlled trials have been. Okay, controlled trials have been done on this phenomenon. Yeah, that's the correct diagram. Corrected version of the same diagram, right? You see that? Okay, next point. Phantom limbs are spooky enough. The converse of the syndrome is even more rare, very rare. Phantom limbs are common, but the converse is apotomenophilia. Fancy Latin name. All it means is a person develops the urge, in fact, lifelong urge. From childhood, he has the urge, nurtured the urge to remove his own normal hand, normal arm, perfectly normal arm. You can do neurological testing, sensory testing, all normal. At the age of 70, he came to me, the dean of an engineering school, came to me, perfectly normal guy, fluent in conversation, alert, intelligent, as indeed a dean should be. And then I asked him, what do you want? He said, I want my left arm removed. Right from childhood, I've nurtured this urge to remove my arm. Can you, in the United States, it's illegal to remove a normal intact arm. It's illegal. He said, but what if I go to Mexico? Mexico is illegal. He thought I had some contacts in Mexico. He said, we heard you have some contacts. I said, I don't have any contacts. But I'm happy to take a look and see what's going on. First I did sensory testing, all completely normal. Sensory testing, all normal. Hand is normal. So this guy has this region of the brain, the hand region, arm region, is missing. Electrodes put them on the skin, anywhere on the chest or other arm. Measure the electrical conductance, change in conductance, called GSR, galvanic skin response. I show you tigers and lions, you get a huge jolt in your GSR. You start sweating, believe it or not. Preparing your body for fighting, fleeing, and sex. That's 3 Fs, fighting, fleeing, sex. Okay? So anyway, you prepare your body for action. You sweat to dissipate heat that is generated from activity. So the sweating happens whenever you look at something exciting. Something utterly trivial like a shoe or a chair or a pig, you won't start sweating. But if you see a shoe, if you have a shoe fetish, then you start sweating, but not normally. Now, if you go to the people, when you see looks at strangers, no sweating. But if you look at his mother, there's sweating, which we won't go into later. I'm not going to talk about it in this lecture, but it's complicated, called Clarenbach Syndrome. Every one of you, you look at your mother, you start sweating, believe it or not. You don't have to be Jewish. You can do that. Now, we're interested in apotomenophilia. Question is, if you poke him in the abnormal hand, you should not get the same. We tried this in the laboratory, a couple of hours of experiment. Poked him in different parts of the arm, measured the skin sweating. Poked him in the abnormal part, normal part. No difference in skin sweating. There goes our theory. Kaput. The amount of autonomic reaction, skin sweating, is the same whether you poke him in the offensive part or a normal body part, right? Inferior parietal lobule in the parietal lobe, IPL, inferior parietal lobule, which is concerned with constructing a body image. Now, I have this vivid image of my body. I'm standing here, proprioception, my muscles, my joints send signals, vestibular system sends signals to my brain. Very dynamic activity. Standing is very difficult. You think standing is a passive activity, you try removing somebody's brain when you're standing. Top of the brain, he'll fall down. Obvious, right? So standing is equally, it requires muscle antagonistic, agonist muscles contracting rapidly. Anyhow, so this is going to that, and that region of the brain, which has a complete map, polysensory map of touch, vision, hearing, vestibular sense, that map is missing the hand. That's what we found. Yay! That means the signal goes all the way, processed normally, normal skin, normal receptors, normal thalamic, normal cortex, S1, S2. When it goes to IPL, inferior parietal lobe, no place for it to go. This acute discrepancy. Signals arrive, there's no place, creates anxiety. Brain abhors discrepancies. Anxiety is picked up by amygdala and limbic structures, amygdala, insula, limbic structures of the brain, the emotional core of the brain. And the patient says, this is abhorrent. He can't make any sense of it. There's a vague sense of unease with his arm. Then when you amputate the arm, 2/3 of these people get their arm amputated. Believe it or not, get arm amputated. And they're happy. Depression lifts. For the first time in their life, I feel complete, I feel happy. Now, that's extraordinary. You compare this to the Freudian theory of optomophilia. The Freudian theory of optomophilia, which was known before we came up with physiological explanation, is the following. This type is a cry for attention. Remove my arm, doctor. Cry for attention. That's nonsense. Why would you want to remove an arm as a cry for attention? Or why not something, like ear or something? Why the arm? So important to your life. That's nonsense. Okay. Another even more nonsensical explanation is that you want amputation to create an enormous amputation stump. This resembles a gigantic penis. This is the official, I'm not making this up, you go look it up in the textbooks. This is a complete nonsense, typical of Freud. Deep insight into the human condition, but some of what he said is just nonsense. Not everything revolves around penis and sex. Now, a cigar is a cigar syndrome. Okay, now we've done that. What we've taken is a bizarre, seemingly incomprehensible neuropsychiatric syndrome where a patient wants his arm removed, rejected the two Freudian explanations, come up with a circuit diagram in the brain that explains the syndrome. It's relevant to how all of us construct a body image, not just patients. Okay, next thing I want to tell you about is another syndrome, which is again about phantom limbs, but this time is even more interesting. Phantom limbs are fine. Some patients deny the existence of the arm. You get oppositional, I told you about that. We observe, okay, here's interesting. Rizzolatti in Parma, in Italy, discovered certain neurons in the front of the brain, frontal lobe, which are like traditional motor output neurons, which move your hand, touch your nose. These neurons orchestrate the sequence of muscle twitches by activating motor neurons in appropriate sequence. You go and grab a peanut, put it in your mouth. Right? Now 10% of these neurons will not only fire when you reach and grab a peanut, but when I watch you, anybody here, but I'm just picking on you to illustrate. When you reach for a peanut, that same neuron fires. This is not some psychic phenomenon, it's not telepathy or anything like that, because the neuron is taking the visual input, transforming it into an abstract, modality-free representation of reaching behavior, because the same neuron is firing if you were to reach, right? The brain is saying, he's up to the same thing as I would if I were to reach the peanut. Therefore, he's intending to reach a peanut. His impending movement towards the peanut is inferred by activity in mirror neurons. So it's constructing a theory of a person's intentions, theory of mind. Other persons are intentional beings, very important brain function, mediated by these neurons, mirror neurons, okay? Another group of mirror neurons, sensory mirror neurons, very different. They will, the back of the brain, parietal cortex, the diagram I showed you. Yeah, the diagram I showed you. Just in front of it, there's another area called V2, S2, somatosensory 2. S2, 10% of the neurons will fire when I watch, so let's say I watch you. When you stroke me with a needle or poke me with a needle, I'll say ouch and withdraw. But when I poke you, same neuron fires. Now that's astonishing. Why would a neuron, sensory neuron fire when you're being poked? Again, it's doing a virtual reality simulation of your impending move, of your impending action, and of sensations associated in his brain with poking. So the neuron fires, and you say that's what he's experiencing the same thing as I would experience if somebody were to poke me. Empathy, the beginnings of empathy, are right here in the mirror neuron system. Now, interestingly, mirror neurons are also involved in more complex types of empathy, not just sensory. More complex. We can get to that later. Origins of imitation, indeed of culture, civilization, all of that may depend on mirror neuron. You don't want to overstate the case, but to some extent they depend on mirror neuron. Okay. Now, how do you study a mirror neuron? We said, okay, simple question. Any engineer would ask. Any scientist would ask. If I were to poke you and I get a response from a neuron, and I poke myself with the same neuron firing and I withdraw my hand, how does the brain know which is who? Why does the brain not react with actually feeling pain when he's being poked? Ow! Somebody pokes you and say, ow! I don't do that. You'd think I was crazy if I did that. I empathize, but I don't literally feel his sensation, even though the same neurons are active. Why is that? It's because, we said, his normal skin is telling him, null signal, saying, no, shut up, there's no pain here. So part of the activity of the mirror neuron system is silence. The null input that's coming, you being poked with a needle, does not shout in spite of the neuron being stimulated. Because of vetoing from skin receptors. Your own skin is telling your brain, you poke your face with a needle, or your hand with a needle, signal goes to the brain, your brain says, my hand is being poked. There's nothing negating that, no contradiction from the skin, because there's no skin there. Therefore you feel the pain, literally, when your amputee watches another person being poked in his hand, he literally feels it. And sure enough, that's what happens. 3 out of 5 patients, you go and study them. I said, ow! He shouts. He doesn't merely say, I get sensations in my body. It's like you've dissolved the barrier between human beings. The only barrier between you and me is the bloody skin. If you remove the receptor skin, then I dissolve into you, you dissolve into me. That's why I call it Gandhi neurons. It doesn't respect the distinction between self and others. The brain does not necessarily respect in all situations. And okay, Gandhi neurons are fine. It's involved in imitation, all of that. Long story. But clinically, is it useful clinically? Yes, because patients often have cramps in the phantom hand. Cramps or scratching in the phantom hand. Itching. How do you treat that? He can't scratch a phantom. Right? He can't scratch it. Doesn't work. What do? He watches his wife, the physician, massaging his hand. Real hand. He gets a phantom massage in his phantom hand. And the pain goes away. This has been studied now in clinical trials. Walter Reed. It works. Now you have true treatment. You have mirror treatment for phantom pain. You have vicarious massage, watching somebody else. Extraordinary. We also see people who are congenitally have this condition, which we call interpersonal synesthesia. Interpersonal tactile synesthesia. Me feeling your sensations directly. Congenital variant of this, you see it right from childhood. The woman says, I've always felt other people's sensations. I dare not tell people. They'll say I'm this crystal lady and mumbo jumbo and psychic. I don't want to tell them, but I really feel this stuff. You believe me. I said, I'm not sure. Let me test you. So bring her into the lab, and I do various tests to show she's really feeling the sensation. How do you test that? How do you test? Somebody comes to you and says, I'm not merely imagining the pain. I literally feel the pain, as if you're poking my hand. How do you test that? Very simple. Or do anything to me, I feel it in my body. Wherever you touch me, I feel it in my body. How do you test it? Okay, you bring the chap. You can't just ask him because he might lie in insurance or for attraction. Per patient sitting here, with this phenomenon, it's called interpersonal interpersonal sensory synesthesia, tactile synesthesia. Patient sitting here, runs in families, by the way. So one of her parents has it, she's sitting here, and I say, okay, here's another colleague, a medical student sitting here, watching. And I hit the medical student in the face. I pretend to. On occasion, I've overdone it. But never to the point of causing harm. But what do you normally do when I do that, suddenly? Anybody, what do you normally do? You blink, close your eyes, withdrawal reflex. You can't avoid it. Now this person here is you're not doing anything. She has a syndrome. You hit me or hit this student, she winces and withdraws. Normally a person will get a startle reflex. You get a startle because it's sudden, but you don't get a withdrawal, closing eyes withdrawal. She does that, showing that very likely she's experiencing the sensation. It's not made up. So simple observation like that can give you the clue. You don't need to do 5 years of brain imaging and spending thousands of dollars and getting ambiguous results. This is what happens. Next experiment. Okay, what about heat? Will it be referred? If I put a boiling water in front of her, dip my hand in boiling water, and she's watching me, will she feel the boiling water and will she withdraw her hand or shout or scream? Will she feel the pain in the boiling water? Okay, I'm going to do it. I put dry ice, pretending it's boiling, just dry ice, carbon dioxide. Put fake flames in it, so see. And I say, I'm going to put my finger in this, I'm going to watch it. I'll watch it, doctor, but don't do it, Rama, don't do it. I said, don't worry, I just briefly dip it. I'm used to it. Okay, do it. Plonk, splash. She's puzzled. She said, well, I feel the splash, the water. I don't feel the warmth, the temperature. This is because there's no temperature mirror neurons. There are only touch mirror neurons and pain mirror neurons, no temperature. Okay? That explains that. Now, interestingly, another observation. I was talking to her. Her hand, it experienced a splash below the table. What was she doing? What was she doing with the hand? Anybody guess? She was doing this. And I couldn't see it until I bent my head. Why was she doing that? Because the wetness, she thinks it's still there. She's trying, no hand there, but she's shaking her hand, right? But the pain, the temperature, is not referred, and unless she's very clever, she's trying dysfunction, malady. Deafness, malingering deafness, very common for insurance. Malingering deafness, pretending you're deaf. You can talk to the guy and he doesn't reply. Puzzled look. How do you prove that he's deaf? Very simple. You drop a coin, irresistible urge to look at it. All human, rich or poor, the reflex, money, ocular orientation reflex. Right? So you know immediately he's lying. Similarly, you have to do simple tests first before you launch off a detailed experiment. Okay, finally, these people are more empathetic than run in families. They're much more empathetic than normal people, because hyperconnectivity between limbic structures, emotion structures, and other parts of the brain leads to hyper empathy. They cry when you have some minor problem in your house or house. They start crying. So it gives you a window of opportunity to study empathy. The neurons allow you to study empathy. Now, finally, you can actually tickle yourself. She starts giggling uncontrollably. I told you this earlier. Why would that happen? Normally, you can't tickle yourself because there's a perfect match between command and feedback. You need a mismatch to produce laughter. But if you tickle yourself, she doesn't know how you're going to do it. But she feels the tickle because of this phenomenon. She laughs uncontrollably. Interpersonal gagglesthesia, we call it. Just because it's a fun, long name. Okay, that's so far so good. Now, last part of my... I wouldn't have thought you could learn so much about what's going on here. Oh, I see it. Neurology or neuropsychiatry, because some patients come up with all sorts of strange symptoms which are inexplicable but bogus. They're just making it up. I'll give you one example of this, or 3 examples I'll give you. Sometimes you figure it out and it's a real syndrome. Most of the time the patient is not lying. It just means you're not smart enough to figure it out. Most of the time. Sometimes they do make it up. Do Clarenbach Syndrome. What anybody here knows who will not come to my lecture yesterday know what do Clarenbach Syndrome is? Anybody? Do Clarenbach Syndrome refers to a young woman who develops a delusion that a rich, handsome, famous gentleman, powerful gentleman, is madly in love with her but is in denial about it. It's complete nonsense. There's no such syndrome. Just talking, right? No such syndrome. Funnily enough, there's no equivalent name for equivalent male syndrome. When an aging male develops a delusion that this young hottie is in love with him, but is in denial about it. That's much more common, by the way. It doesn't have a name because psychiatrists are all men, usually. Now, second syndrome is even more silly. Chronic underachievement syndrome. It's supposed to be prevalent among teenagers. It used to be called stupidity in my time. Stupidity is not a syndrome, it's just a phenomenon. Forget about that. Third one is the best one of all. Third one is the best syndrome. Oppositional defiant disorder. Officially defined in DSM-3. Oppositional defiant disorder means the spirited youngster dares to challenge the authority and diagnosis and authority of an authority figure, such as father, mother, sometimes, teacher, or psychiatrist. Now, the man who invented this disease, psychiatrist, was a genius because any attempt to protest the diagnosis can itself be seen as additional evidence for the syndrome, the diagnosis. So you know, no-win situation, right? You can't say, I don't have the syndrome, because then that proves that you do have it. So, okay, but you have to be careful, but usually we are able to sort it out and figure out what's real, what's not. Mirror neurons, I already told you about. Last syndrome I want to tell you about, synesthesia. Galton, Charles Darwin's first cousin, explored the mind. He was interested in exploring the mind. He was also a bit of an idiot. He thought that the races, obvious races, right? You go and read his stuff. But in spite of that, he was a good scientist. Made some important discoveries. For example, he said that certain proportion of the population, 1 out of 10,000 people, 1 out of 1,000 people, has the following quirk. Every time they see a number, they see a color. 5 is red, 6 is blue, 7 is 8. Every number has a color associated with it. Now, nobody could prove this. He just gathered this evidence and said this is what people feel. First of all, we found it was much more common than he thought. 1 in 100 people has this phenomenon. When you see numbers, you see colors. You then figured it out, what's going on in the brain. Why should you care? I'll get to that in a minute. We figured out that, for example, that it's a real phenomenon by putting this array. 2 is red, 5 is green in these people. How do you find out he's really seeing it? You put this array. Normal people have a difficulty in finding a triangle in that. How many of you see a triangle in that, embedded in that? Nobody. Okay. Now, if you're synesthete, you see that. You see, because 2 is red, you see, I see a triangle. I see it much more quickly than all of us. This means it's a real sensory phenomenon, perceptual qualia being generated, and it's not some, conceptual link between number and color, but actual perceptual. He sees it clearly and pops out at you. How can something that's a concept pop out? It pops out perception. You can measure reaction time and show it's real, but I won't go into that. What part of the brain is involved? Second question. In fusiform gyrus in the temporal lobe, there are two areas, one area for color, one area for number, right next to each other, touching. What is the likelihood that number color synesthesia is the most common type of synesthesia, and these two areas are right next to each other in the brain? Very, very unlikely it's a coincidence. So let's do some brain imaging. Sure enough, with Ed Hubbard and Boynton, we showed that if you do brain imaging, color area and number area are sitting right next to each other. In synesthesia, you show black and white numbers, the color area lights up. Normal people, it doesn't light up. So you show anatomy, do psychophysics, and then you say, why the hell is it important? Okay, another good example. I want you to look at this very carefully. Here's a bunch of letters, right? Does it spell out? Can anybody read it? Anybody here read this? Maybe people in the back. Anybody read this sentence? No, Alex, okay, now what you do is you squint your eyes. Squint your eyes like that. Really make it blurred. Right, remove your glasses. Squint. Now do you start reading it? Anybody read it, please? Raise your hands. Wait. It says, I can't read it. No sex causes blindness. No. Bad eyes. No sex causes bad eyes. So all of you should be concerned. Okay, so now if you show this to a synesthete, who sees A is red, B is green, C is blue, he sees a palette of colors. Then he infers, he says, that must be this is blue, it must be an N. This is red, it must be an S. He infers the colors based on the colors evoked, he infers the letters. And then reading kicks in and he reads it. So this means the color is evoked unconsciously, even before conscious recognition of the letters, earlier in the brain, through cross-activation of colors by the numbers. Every time you present a number, adjacent color neuron is activated automatically without you being conscious of it. Then he consciously infers what the letter is. Okay, very important. There are other stories along this line. I won't go into, like story about colorblind synesthesia, oxymoron. How can you be colorblind and be synesthesia? Beautiful oxymoron, which I'll tell you about later in discussion. Okay. Finally, where does it happen? I already told you. Okay, now we get to calendar lines. Galton also said that synesthesia is much more common among artists, poets, and novelists than the general population. Much more common among artists, poets, novelists than in the general population. What do artists, poets, and novelists have in common? Anybody? They're all crazy, of course. No, but they're all good at metaphor, linking seemingly unrelated ideas. It is the east and Juliet is the sun. It is the east. You don't say the sun is a glowing ball of fire. Juliet is a glowing ball of fire. You don't say that. Warm like the sun, radiant like the sun, nurturing like the sun, rising in bed like the sun in the east. Center of my solar system, like the sun is the center of the solar system. All this about Juliet. Shakespeare is a master at this, creating multiple associations. These patients, not patients, these individuals with synesthesia have more connections in the brain because of defective pruning. It runs in families, and ordinarily your brain, everything is connected to everything when you're born, in fetus, and you trim the excess connections to create modular architecture of the adult brain. You trim the excess, create modules that characterize different functions in your brain. If the trimming fails, with a mutation in the trimming gene, then you get cross-activation between adjacent brain modules, like number and color, so you see numbers as colored. Okay? Now, if the gene is expressed throughout the brain, instead of selectively in fusiform gyrus, what do you see? You see cross-activation throughout the brain. Remote regions of the brain, which represent concepts and ideas like women or love or beauty, get cross-activation here, creating a natural propensity towards metaphorical, analogical thinking, which is the basis of creativity. So you started with a quirky phenomenon, synesthesia, where people see numbers colored, gone to the brain, and first of all showed it's real using perceptual experiments, gone into the brain, done brain imaging, seeing what's going on, where it's going, come up with a theory of what's going on in terms of brain hyperactivity across brain modules. Finally pointed out its relevance not only to you and me, but to creativity. Start with this quirk, take you on a journey all the way to creativity and Shakespeare. That's the name of the game. Finally, last 2 minutes, 3 minutes, Galton is also interested in number line, as calendars, how people visualize calendars. When I ask any one of you, visualize a calendar in front of you, and describe it to me, please describe it to me. Just imagine you're seeing a calendar. Go ahead. Any one of you. How about the guy, second, colorful shirt? Normal calendar, yeah. Sorry, just when you visualize it, what does it look like? I'll put you out of your misery. Left, right. January, February, March, April, May, June, July. Calendar. Annual calendar. January, February, March, April, May, June. Boxes. Right. Now some individuals, however, people thought 1 in 1,000, 1 in 10,000. We found 1 in 100. 1 in 50. See a hula hoop in the calendar. It goes clockwise for left-handers, anti-clockwise for right-handers. Why the hell, why would you see a hula hoop? For imagining a calendar, why would you see a hula hoop? January, February, March, April, May, June, July, December. Some of them will see an L shape. December breaks, January, February, March. April, May, June, July, August. Like a Lego. Some of them will see U shape. January, February, March, April, May, June, July, August, September, November, December. U shape horizontal. An L shape. Why? This is a kind of mystery I find fascinating. People thought they were crazy. What do you mean an L-shaped calendar? It doesn't make it. They've never seen one, right? Why would they make this up? First of all, are they making it up? How do you find out? Simple. We said, okay, if this guy is really seeing it in front of him, he'll say, I see it in boxes, January box, February box, March box, actual boxes surrounding each month, and the printed letters, words, December, January, in Helvetica, or Arial, the font he'll describe, it remains constant. And over month after month, constant position, everything. He's had it all from childhood, early childhood, as far back as he can remember. From the age of 2 or 3, not 2 or 3, 4 or 5, remember the calendar being shaped like this. Why would that be? I'll tell you in a minute. I'll solve the problem. Okay, first of all, how do you know it's real? Very simple. You ask him to read the months backwards. Please read them. I'm going to name a number, name a month. You read it backwards as quickly as possible, okay? March. Any one of you. Go backwards. March. All the way back. February, okay, go. You're slower than I thought. It takes 3 times as much time to go backwards. Read forward now. February. Quick. March, April, May, June, July, August. Okay. People are 3 times faster going forward, backward. Now, however, in these patients, the speed is same, going forward or backward, because they're seeing a picture in front of them. It's reading it off. If I showed you an actual calendar, there won't be no difference in left going backwards and going forward. You no longer use an algorithm, use a visual representation, and you read it off, backwards, forward, same speed, and faster than any synesthesia. Sorry, faster than any normal person, if you have synesthesia. Is that clear? Reading back. You can subtract 1 month at a time. January, I can't do it. November, September, alternate one backward. You do alternate one backward. Very difficult. All of these experiments proved in 10 minutes, 15 minutes, that 100 years of controversy about whether it's a real phenomenon is laid to rest. It's a real phenomenon. Take it from me. Okay, next question, what's causing it? Where is it in the brain? Okay. Simple experiment. If you put a vertical rod, a red vertical rod, against a background of tilted black and white grating, take a grating, tilt it 45 degrees, put a red vertical line, guess what happens? Visual illusion, the line tilts in the opposite direction. It's called tilt contrast. Supposed to be due to orientation-specific cells in area 17 in the brain, discovered by human reason. So tilt contrast, you get a tilt of a real line. What if you project your calendar? I told her, project your calendar, your vertical calendar, L-shaped calendar, U-shaped calendar, onto the tilted grating. What happens? Guess what happens? Calendar tilts in the opposite direction, like a real input. So it's behaving like a real, actual physical input, even though it's in your mind. There's no calendar out there. Not only that, she says, this particular lady says she's in U-shape, and I read the January, February, March, April, May, June, July, August, October, November, December. It's funny, I can't read it. What do you mean you can't read it? I can't read it. Already it's telling you he's not making it up. Why would you make up such a bizarre story, right? I said simply on a whim, I said, go behind the calendar and see what happens. So what do you mean go behind the calendar? Just pretend you're going behind, allocentric view. Go behind it and see what you see. Okay, see, I'll try it. I'm struggling, and then she said, oh, I'm behind the calendar now. Oh my God, now I can see the letters clearly. Now I see the mirror reverse when I was on the other side. Now they're not mirror reverse because I'm seeing from the back. But the other letters are not mirror reverse. Why the hell should you see a Mobius strip-like phenomenon with a calendar, with legibility depending on point of view, in our memory, is utterly bewildering. I have some vague ideas about it. Utterly. This shows, by the way, the whole notion that AI chaps, pardon my, no irreverent man, but the computer in the brain, and you compute things, and you have representations, they don't bear any resemblance to real things, obviously. There are no homunculus in your brain. No little guy watching a screen in your brain, obviously. You're creating equations. But if that's true, why is it you go behind a twisted calendar, you read from the other side, you're able to read it. It's almost like a real piece of paper in front of him. Reading, twisting. And other examples of this sort, which I don't have time to go into, but one last example and we're done. Okay, then the question is, why does this happen? That's a big mystery. Why does it happen? Okay, that shows you the tilting effect. I think it happens because you can go to inferior parietal lobule in the left hemisphere. Inferior parietal lobule is concerned with representation of space, representation of left and right, representation of sequence. That's damage ability to sequence things. Sunday, Tuesday, Wednesday, he gets it wrong. quite often, dyslexic children, or interchange letters. Dog, D-O-G, they'll put D-G-O, because sequence is messed up. Otherwise they're quite normal. In fact, they're better than normal in many respects, but sequencing gets messed up. So these people, I claim, have a problem with sequence. And what's more, angular gyrus is center connections which have been mapped out, inferior longitudinal fasciculus, to the temporal lobes where you've got the memory system in your brain. The GPS system was discovered by Nobel laureates just 5 years ago. Brain's GPS system in the hippocampus allows you to get your bearing. You open your eyes in a strange country, strange hotel. Where am I? You get disoriented. It takes a minute to snap back into, because you engage the hippocampal GPS system, then you're back to normal. I'm in this campus and I'm going to go home tomorrow, go eat first dinner. Also, you create a calendar. Calendar is not something trivial. You take it for granted. Part of who you are. Without a calendar, you'll be completely chaotic. Knowing when and where, what you're up to, planning, all that is a vital part of being human. A lot of cultural variation. I'm not saying calendar is entirely neural structure. Cultural variation. Germans, you can't deviate from your appointment by 1 second. I have German friends. Italians, doesn't matter, like Indians, right? It doesn't matter. So clearly there's no genetic difference, there's cultural emphasis on culture. So what I'm saying is you take something as complex as a calendar, and you can do other experiments which, okay, why does it happen, right? Two very general remarks and I'll conclude. One point is that the brain, why does it have spatial representation of calendar? Why not have an algorithm? Lookup table, why does it have spatial? The reason is you can't develop abilities de novo in the brain. Evolution is hacking all the time, using pre-existing structures. It cannot develop an abstract mechanism for time, representation of time. But it has hundreds of maps in the brain, topographic maps of the world. So let me map time onto space. And in maps, you get a calendar. The sequential aspect of a calendar, you get that by mapping. Pre-existing maps, you utilize pre-existing structures, kludge and all that, and then you create a calendar. I'm going to say this is true of every function of the brain. And this is secret. Evolutionary biologists know about, but most other people in my field or any field know about, which is that the brain often uses tricks, shortcuts, heuristics. Even worse, the evolutionary trajectory, we don't know what that is, of a particular symptom or a particular function of the brain. For example, you'll all be astonished if I tell you, where does hearing come from? Where does hearing come from? Anybody know where hearing comes from? Quickly, running out of time. Hearing, where does it come from? It comes from chewing, mastication, and from cells on the side of the fish body, hair cells. These get, in the Devonian period, fish are swimming, picking up waves for schooling and dodging predators. This part got pinched off into the skull, into a sac called the ear. Then you need to amplify the sound because impedance changes. You invade land, you're an amphibian. So fortunately, your jaws are on the ground, reptile and amphibian. This transmits the sound into the sac. So the impedance matching is achieved spontaneously, and you hear normally. Now that's not enough. You come to land completely, become a mammal, you're on all 4 feet upright, jaws are no longer on the ground. So how do you solve the problem? You incorporate 2 of the jawbone of the reptile has 3 bones. To swallow a big prey, low metabolic rate, has to swallow a big prey, and sleep for 6 months. Right? Another antelope, that's his lifestyle. But his mammals are scurrying around and eating all the time, feeding all the time. His low metabolic rate permits the opening up of the jaw, and then the 2 hind bones can be incorporated into the ear, amplifying the sound, conveying it to the eardrum, allowing you to hear. Nobody in his right mind will conceive of such a situation, not even God, will conceive such a trajectory in evolution, that from the jawbone. So each of you, when you listen to something, you're going back to the Devonian seas. The hair cells in Devonian seas are vibrating. That's what's going on each time. That's a very, to me, it's a very astonishing thought. So this, what I didn't mean talking about jaws, is equally true of brains. Every brain module, every elaborate function, language, perception, went through this extraordinarily complicated mess trajectory. Until you understand the trajectory, you won't have a complete understanding of the brain function. That's the point. Thank you.